So now let's start with what I'm going to talk to you about is the numbers here, right? And we know that the numbers. So let's start with the square numbers. Okay. So we know that I mean, if you write the multiplication table, you know that the diagonal is going to give you the square number, right? Like 1 square, 2 square, and then so on. But let's say that we have this square number, and if you want to take a look at this in mod 5, right? So for example, if I write the numbers in mod 5 means the possible remainders when you divide it by 5. So let's say that I'm gonna write the numbers in this fashion: 0, 1, 2, 3, 4. Now we have 5, 6, 7, 8, 9. Then let's take a look at these ones, right? Okay. Again, I'm writing this in mod 5. Okay. And then we have 15, 16. So like I'm gonna circle the one in mod 5. Okay. I'm writing the numbers in terms of, as you can see here, column of 5, right? So we are gonna look at the square numbers in mod 5, okay? And then if we continue here, let me write it in this sense here, 25, and then so on, okay? And then I will just stop, I will not write the whole thing, but I will just gonna stop it when I reach 49, okay? So let's take a look at this number, right? And now I'm going to circle all the squares here. 1 is a square, 4 is a square, 9 is a square, 16 is a square, 25 is a square, 36 is a perfect square, and 49 is a perfect square, right? Okay. If you want, we can actually go to, I didn't want to do that, but let me go all the way to 64 here. Right, and then we have, okay, so now, and then 64 is also a perfect square. So if you take a look at here, in mod 5, we can see that the perfect squares here, right? So as you can take a look at here, the perfect square 0 and 25, it can be equal to 0, it can be equal to 1, or it can be equal to the remainder of 4, right? Okay. So we know that in mod 5, perfect squares can only be 0, 1, or 4, right? Because as you can see, this column, you're gonna have, it's all empty, right? Okay. If we do the same thing, for example, let's say in mod 7. In mod 7, right, the perfect squares will either give us a remainder of 0, 1, 2, or 4, okay? And in mod 8, the perfect squares is gonna be, the perfect squares are only gonna be 0, 1, or 4, right? Okay? So these are just, I mean, why did I pick 5, 7, and 8? Just, I mean, there's no apparent reason, okay? So what we do is that now, by the way, I will open the chat from time to time, okay? So for those who have any questions, okay? So we know that again in mod 5, we can see that if you do this the same thing in mod 7, if you go from 0 to 90, and in mod 8, let's say if you go from 0 to 103, we can see that, and if you mark the perfect squares, the only columns that you are going to be marking are going to be 0 in mod 8, 1, or 4 in mod 8. So we can see that this is important. All squares are always going to be 1 in mod 8, right? Okay. So all squares are going to be congruent to 1 in mod 8. Okay. Now, yes, let's not spam. Okay, I will turn it off, of course, guys. Okay, I just want to turn it on from time to time so they can get it out of your system. Okay, okay, to write something in the chat. So now, let's take a look at, oops, sorry guys, there's a little bit of lagging. Okay. Now, so what I will do is that, so let's say that we have, let's say we want to write the numbers in rows of increasing length, okay? Okay, so we're gonna we're going to write, for example, let's say that I want to have a, let me use another color here. I'll use the blue one. Okay. Let's say I will have a circle here, and then another circle, and then another 3 circles, 4 circles, 5 circles, and then so on, right? So now, what happens is, so if you write the numbers in rows of increasing length, right? So that this is gonna give us what? The triangular numbers, right? So what happens is, in here, we only get 1, right? But now, in here, how many do we have? 3, okay? And then, look at the one that's, look at the one in green. In here, we have total of 6 numbers. Look at the one in the black. We have total of 10 numbers. I'm sorry, 15. Oops, is that correct? 15 numbers. 10 numbers. And then the last one, we are going to have, let me show that with blue on here. For example, we are going to have 15, right? And then you can see that all these numbers are going to be, is called the triangular number, right? And we call so we're going to call, let's call the n triangular number, let's call it with delta n, right? Okay? And we can see that the sum of the, so now the triangular numbers can be written in the form of what? So we know that the triangular numbers can be written in the form of 1 over 2 times n plus 1, okay? So now, and from here, we can also say that twice the triangular number is called, maybe you guys heard of it, I don't know, it's called pronic number, okay? So pronic number means, oops, sorry about that, oops, another class, okay. So now, when we say that the pronic number here is twice the triangular number, and therefore it is n times n plus 1. So basically, product of 2 consecutive integers, right? That's what we call it, okay? I have makes sense. Okay. So now, by the way, you can show that this is true by using induction, right? If we show that this is true for n minus 1, right? And if we add n to both sides, we get the sum of the triangular numbers. You can show the proof by using induction, okay? The mod means the remainder when you divide the number. For example, it is called the residue, or it's called when you divide by 5, for example, we get a possible remainders are 0, 1, 2, 3, or 4. So when we say about mod 5, that's what we mean. Okay. Okay, so I hope that makes sense. Okay, so now again, twice the triangular number is going to be the product of 2 consecutive figures. Okay, and now we know that because 2 consecutive numbers, one of them has to be even, is always divisible by 2, right? So therefore, the triangular numbers are always integers, right? Okay. I hope that makes sense. So now, by the way, by using this, we can also show that sum of the first and odd numbers is going to be equal to, so for example, if I add 1 plus 3 plus 5 all the way to 2n minus 1, okay? This is going to be equal to what? This is going to be equal to n squared, okay? So this is the sum of the odd numbers. And also, we can also find any arithmetic sum of any arithmetic progression, right? Or a sequence of n, okay? So what we can do is that, again, we can say that, for example, let's say I have an arithmetic progression. This is just as a note. Let's say my arithmetic progression is A, B, C, all the way to X, Y, Z, okay? Arithmetic progression means that the sequence, the difference is gonna be, they're equally spaced, right? So if I have the sum of n equally spaced number with the first term A, the last term Z, then we know that the sum of them is going to be n times the average, right? So the sum of A plus B plus C all the way to X plus Y plus Z. Again, there are n numbers here. Okay, let's say we have n. Okay, this is going to be n times, it's going to be n times A plus Z over 2. Okay, and this is an arithmetic sequence. Okay. Okay. It's going to be a plus z. Okay. Again, I will allow the participants, I will allow you to chat, guys, so you can write if you have any questions, okay? And now, so let's see what happens if we keep adding the cube. By the way, we will go over a few questions on triangular numbers, okay? Hello, people. Wow, so many people writing so quickly. Yeah, okay. Let me, so I guess no one has a question, so let me. Okay, so I stopped the chat again, okay? Okay, so now, what you're gonna do is it, so now what I will do is I'm gonna write the sum of 1, 2, 3 for the consecutive odd number, okay? The sum of the consecutive numbers starting with 1, and we are gonna see that it's gonna give us the scoops, okay? It's gonna give us the perfect scoop. Okay, and but before that, let me go back to the triangular numbers here, okay? Because that is gonna be important. We're gonna solve some questions regarding the triangular numbers, okay? Now, what we know is that, so we can see that the sum of two consecutive triangular number is going to be a square. Can someone see why that is? Let me show you why that is. I'm going to repeat it again. The sum of two consecutive triangular numbers is going to be a square. Why is that? Because what happens is when you, okay, so when we flip this, it's going to form a square basically, right? The sum of two consecutive triangular numbers. So for example, let's take a look at, oops, sorry, again, it's lagging a little bit. Okay, so let's say that our triangular number is nth triangular number and then n minus 1, right? Okay, so you know that the nth triangular number is going to be 1 plus 2 all the way to plus n. And then n minus 1 is going to give us what? 1 plus 2. And then all the way to what? N minus 1, okay? So now, this is the nth triangular number, and this one is this n minus 1 triangular number, okay? And now, let's see how I will add these ones, right? So I'm gonna add it in this form, 1 plus 2 plus 3, all the way to n. And then I will write the other one, 1 plus 2, and then all the way to n minus 1. Then if I add these, right, I get 1 plus 3 plus 5, all the way to 2n minus 1. And remember, we just said that the sum of the first n positive odd integers is equal to n squared, right? So we just showed that the sum of the two consecutive triangular numbers add up to a perfect square, okay? I wanted to. Now, the other question that we see, okay, again, I will allow people to chat so you guys, you guys can write if you have any questions, okay? Again, I just showed that the sum of two consecutive triangular numbers is a perfect square, okay? Guys, please stop spamming, okay? I just want to see, I cannot see the questions, okay? And I don't want to call the names, but okay, so let me write again. Ethan, this one is for you. Okay. Okay, guys, so now I will not, yes, the chat is recorded, by the way, and the meeting. Okay, if you have any questions, guys, I will only, okay. You can only write to me, guys, okay? So please, Nathan, same with you, Nathan, same, okay? Yes. Harshila, I'm listening. is mod 5. Yes, Raj, I'm listening. Yes, I'm gonna, benzo will not be allowed either. Okay, so now let's continue with the, okay, I will answer that question again, okay? So now, yes, so what I said was, the first, we know that this one is the first triangle, like this is the nth triangle, and so that means the triangular number means the sum of the numbers up to n, right? So I write them as 1 all the way to n. And then the previous one is also all the way to the previous one before the nth one, which is the n minus 1, is also from 1 to n minus 1, right? And then what I did was, I write them out in this form, 1 plus 2 plus 3 and so on. And then I write the next term here, like this form, plus 1 plus 2, so I added 1, 2 plus 1, that is 3, 3 plus 2, that's 5, and all the way to n plus n minus 1. And we can see that these are basically all the odd numbers up to nth odd number, okay? So now, this is one test, so that means the sum of the n odd number, the sum of the first n odd number is going to be equal to n squared, okay? So now, let's move on to the, so let's see that we can also see with the triangular numbers that some of the triangular numbers are perfect square. So let me write this first triangle. We have 0, 1, 36, 12, 25, and then so on, right? So we know that this one is the first triangular number, right? And this one is going to be the what? It's going to be the sixth triangular. I'm sorry, not the sixth one, the eighth triangular number, and so on, right? And then, so we can see that there are some triangular numbers that are perfect squares. But how can we figure those out, right? How can we know which triangular numbers are perfect squares, okay? So now, we can see that with the triangular numbers, remember, they can be written in the form of n times n plus 1 over 2. So this is, remember, this was the nth triangular number. And this is equal to, I want to see which perfect square, right? Okay. Now, what you're going to see is that, so let's see which of these are, how do we find which one is going to be the, so now, if we expand this, we can see that n squared plus n is equal to 2m squared, right? Okay. Now we can see that 2m squared minus n squared is equal to n. So from there, we want to see, okay, well, okay. I hope that makes sense. Okay. Now, again, our goal is, or we can just leave it like, let me go back again. So we know that we want this one to be a perfect square, right? Okay. Or this is going to be the same as, so the one that will help us find which one of these are perfect squares to find us to solve integer solutions is something called Pell equations. Okay? We are not going to get into those here, but we can show that, but I will give you a general form, okay? Sorry guys, 1 second, again. So now, let's see the triangular numbers that are perfect squares, okay? Okay, so we know that again, we want this number here, like we know that this is a perfect square. Let me see, we can see that it's equal to m, or doesn't matter, right? So we know that here, let's call that this number, let me call this number as like m, okay? We want m to be a perfect square. right? Okay, and then okay, we want this one to be a perfect square. And so that means m is both a perfect square and a triangular number. Okay, now we can say that here we have n squared plus n is equal to 2m. Let me write it in this form, okay? And then now we can say that here, if you solve the quadratic equation, right, plus n minus 2m is equal to 0. With the quadratic equation, we know that n is equal to 8m plus 1 minus 1 over 2. We know that here, this number n is a triangular number and n is an integer if this whole thing is 8m plus 1 is a perfect square. Because if 8m plus 1 is not a perfect square, we will not have an integer here, right? It has to be a perfect square, and it has to be, when you subtract 1, it has to be divisible by 2, right? Otherwise, n would not be an integer, okay? Is that okay, guys? So that means a square number. So in this case here, again, we want 8m plus 1 is a square, right? Okay. So now, from here, because we want 8m plus 1 to be a perfect square, let's call k squared, right? Okay. I hope that makes sense, right? Again, you want 8m plus 1 to be a square, right? Okay. So now, again, what we said was, first, I said that this one is a perfect square, right? M is a perfect square. And then, okay, so let's say that M is a perfect square. Let's say it is 8, some perfect square. Let's say it's a perfect square. Let me pick a number, r squared plus 1 is equal to k squared. Remember, M is a perfect square, right? Which is, I'm going to represent it as r squared. And then we also know that 8m plus 1 has to be a perfect square. So therefore, we can say that we can write this in the form of, this is the k squared minus 8r squared has to equal to 1, okay? So this is called the Pell's equation, okay? Now, the Pell equations have trivial solutions when we have, we can see where is this, where the solutions are. But again, we can, this has to be the case for a triangular number to be a perfect square, okay? And now, few instances that we can figure out in this case here is gonna be, for example, okay? So for example, we can say that this is a perfect square, and then the first triangular number, the 8th triangular number, the 49th triangular number, and then we also have something 288, because I can show you what this means. Let me show the triangular number in the other part here. So for example, let's say triangular 1, right? We can see that this is 1. Triangular number 8, it is 6 squared. Triangular number 49, I can show it with T if you want. Let me show it with T. T1, T8, T49 is a 35 squared. And then 288, it is equal to 204 squared. And then I can go one more, it's 1681, 1189 squared. So these triangular numbers are perfect square. 8th triangular number, 49th triangular number, and then so on, okay? This is 35, right? Okay? Okay. So now, by the way, notice the indexes here. They are either perfect square or 2 times a perfect square, okay? They are either square or doubles of square. Oh no, 8m plus 1, what we meant is that this thing here, this square, because we want n to be an integer, right? Because it is an integer, when this is odd minus 1 is even, so therefore it's divisible by 2. Do you mean, okay, I will explain it after class, okay, Jerry? Okay. I hope that makes sense, guys, okay? So now, again, the perfect squares, so what I mean is this, so let me explain it one more time. In here, this is a triangular number, right? This is how we can represent a triangular number. Let's say this one here, we can say it is equal to n. We can say that n squared plus n is equal to 2n. I basically multiply both sides by 2. And by quadratic equation, we get that n is equal to this, right? And because it is equal to this, and because n is an integer, therefore 8n plus 1 has to be a perfect square, because this is a square root, right? If it is not a perfect square, n would not be an integer. For example, if you say 8n plus 1 is 17, then the answer is square root of 17 minus 1 over 2, but n is not an integer, right? So therefore, 8n plus 1 has to be a perfect square. So this is what it means. 8n plus 1 is equal to a perfect square. But because of I'm looking for the triangular number to be a perfect square, I also know that n is also a perfect square. So we get that 8r squared plus 1 equals k squared. So therefore, this has to be the form. And this is called the Pell equation here. Okay? The form of a Pell equation. Okay? So it has to be in this forms. And in this case, I just give you the examples of perfect squares, okay? Perfect square numbers that are also triangular numbers. M and N are any number that it works, right? Okay? Because that's what I'm looking for. What I'm looking for is which triangular numbers are perfect square. That's what I'm looking for, Angelica. Does that make sense? Because the question is, which triangular numbers are perfect squares? So I'm looking for this case, n times n plus 1 over 2. Can it be equal to 1? N times n plus 1 over 2. Can it be equal to 4? N times n, because I'm looking for, I want it to be a perfect square, right? I'm looking for which triangular numbers are perfect squares. N times n plus 1 over 2, and that is equal to 16, for example, right? Or you can say, can it be equal to 9? Okay? I hope that makes sense. Okay? I hope that makes sense. Okay, guys? So what we are looking for is this. So let me do it again. Okay? So what I'm looking for is, I am looking for n times n plus 1 over 2. Can it be equal to 1? The perfect squares. Can it be equal to 4? Let me write it in this form. 1 square 1. 2 square 4. N times n plus 1 over 2. Can it be equal to 3 square? N times n plus 1 over 2. Can it be equal to 4 square? Okay, so eventually I'm looking for n times n plus 2 is equal to n, which is a perfect square. Okay, I hope that makes sense. Is that okay, Angelica? Okay, so now that's what I'm looking for here. Okay, and I'm looking for to see, for example, can it be equal to 4? Can n times n plus 1 is equal to 8? So you're looking for n squared plus n minus 8 equal to 0. But you can see by using the quadratic here, right? Negative b plus, okay? I cannot have minus because it will be negative. It's going to be equal to 4 times a, okay? 1 plus 4 times 8. Okay? And then divided by 2, right? So that is why I'm looking for, but this is not an integer. So we can see that it's not going to work, right? Okay. For example, let's take a look. Is that okay? I hope that makes sense. Okay. It's Pell equation. For those who ask how do you solve the Pell equation, first you're going to look for the trivial solutions, right? So the Pell equation is in the form of x squared minus, like as you can see here, x squared minus 8y squared is equal to 1, right? That's what, or we can say that 2y squared is equal to 1. Doesn't, like in this case, is 8y squared, okay? So we can see that in this case, this is an instance where the, in this case, n is equal to 8, okay? I hope that makes sense. Pell equation is basically like, it's like a Diophantine equations. We are looking for integer solutions. So any form is in this form, right? But in this case, we are looking for when n is equal to 8, okay? It is a non-square integer, and then we are looking for integer solutions for x and y. Okay. I hope makes sense. So the solutions, right? Well, one thing is we're gonna find the fundamental solution, right? Okay, guys. So in this case here, I think you ask, how do we solve this one? So the form of Pell equation is this, when n is a non-square integer, okay? Now, we are gonna see that, for example, in this case, oh, you're asking how I found this, I think it was Vivian, okay? Why 8? It's because of this, why? It's because of this one is 8. The reason that is 8 is because in the triangular number, we do 2 times 8, right? Remember when we solve the quadratic is b squared minus 4ac. So in this case, we multiply the negative 2m by negative 4. That's why it's 8, okay? I hope that makes sense. That's why this is the form of a Pell equation when n is equal to 8. Okay? But again, we will not go over the, so in this case, we know that here, because this is the form here, right? So we know that you can get x, like, for example, 2a plus 1, y is 2b, and then you get the numbers a and b by halving the denominator and rounding of half the numerator. So don't worry about how to solve the Pell equations, okay, Pell equations. I just mention it because this is basically where it's come from, like how do you find the triangular numbers that are perfect squares, okay? So now, let's take a look at few equations with the summations here, okay? For example, let's take a look at, sorry, let me go to number 1 first. Oops, sorry guys. Not this one, this one. Let's try this problem here, right? The sum of n consecutive positive integers is 1000. And the question is, what are the possible values of n? Let's try this problem here. Guys, don't worry, I will just know. Okay, so I'm not allowing chat anymore, okay? Okay, so let's try this problem here. Okay, so for those who use the language, I'm removing them, and then you will not be able to attend it. So those are removed. Okay, and then let's see. Anyway, so let's see other ones here. Okay, so I removed the ones that are using profanity or inappropriate language, okay? So the sum of n consecutive integers, let's start with positive here, okay? Let me write positive here, just for the time being. The sum of n positive consecutive integers is 1000. What are the possible values of n, right? So now, I start with any number, so I have n. Okay, I have n numbers. Okay. So let's start with a. Then the next one is going to be what? A plus 1. The next number is going to be what? A plus 2. All the way to what? A plus n minus 1, right? So now I have n number of consecutive integers, okay? Now in this case here, we want the sum to be 1000, right? Now the question is, what are the possible values of n? Okay. First of all, we can see that the sum of n, because if you look at these a plus 1, how many a's do I have? I have n number of a's, okay? And then plus all the way to 1, 2, all the way to n minus 1, and that is equal to 1000. Okay? So I have n times a, then 1 through n minus 1, that is equal to n minus 1 times n divided by 2, right? And that is equal to 1000 again. Okay? So now, let's multiply everything by 2. I get 2na plus n times n minus 1, and is equal to 2 times 1000. Okay. Now, what I can say is that let's factor n here, right? If I factor n, I get what? I get 2a plus n minus 1, and that is equal to 2 times 1000, okay? We know that n is a positive integer. I mean, we know that, yes, you know that n is an integer, right? It is a positive integer. And then we also know that, n is a non-negative integer, and then a is an integer as well, right? We are looking for, because I started with 0, right? If I started with 0, I have to go up to n minus 1. Okay. And now here, we know that I'm multiplying two integers. So here, we have an integer. Here, this is also an integer, okay? So now, I can see that, so product of two integers is gonna be, positive integers, it is gonna be 2 times 1000, okay? So now, we are gonna solve for those possible integers. Okay, so now let's continue here. Now in here, we can see that 2000 is going to be equal to what? In here, so I'm going to multiply two positive integers, and I will get 2000. So that means I need to figure out what possibilities we can have here, right? Now you can see that this is 10,000 is 2 cubed times 5 cubed, right? So it's 2 to the 4 times 5 cubed here, okay? Now, let's take a look at what's going on in this part, right? So for example, the possibilities can be, I can have 2 here, and then I can have 1000 here, right? Or I can have 16, okay? And then I can have 125. But we are gonna see which ones are gonna work, right? Okay? Now let's check it out, okay? So for this time, now we're gonna look at the parity, right? So for example, we know that 2a is always even, right? And now we're gonna see what happens when n is odd or when n is even. So let's say that n is an odd number. If n is odd, n minus 1 is gonna be even, right? So that means I will have something odd times even, right? So that's the only one that's going to work there, okay? Now, if n is even, right? Now that means this is an even, and then you can see that this is always even, so it doesn't matter, but n minus 1 is odd, right? So we can see which ones are going to work here. Okay? So now let's see what's going to happen. So we have odd times even, okay? So let's say that n is odd, right? We can try that part. If n is odd here, so for example, n is 1. And then we can see that here, this is going to be 1 times 2000, right? Because it's 1 times 2,000, you know that this is 0. So what is 2a going to be? Then 2a is going to be 2,000. A is 1,000, and that works, right? You just have one number that is going to be 1,000. Now, let's say, in this case here, let's say n is an even number. Let's say n is 2, right? If n is 2, then I know that here is going to be 1,000. So that means we will have 2a plus 1 is going to be 1,000. But we can see that this is not possible, right? Because 2a, we can see that this has to be 2a, has to be an even number for a to be an integer. So we know that that's not going to work, okay? Is that okay? I hope that makes sense. For example, let's try the next one. Let's try if we can have 4, right? If this is 4, so you know that this is not going to work. If this is 4, then we know that the other, now 2,000 divided by 4, we can see that this is 500, right? If that is 500, then we know that 2a plus 4 minus 1, which is 3, is 500. But we know it's not possible either, because 500 minus 3 is an odd number, and that is not divisible by 2. So this is not going to work. But let's try the next one. Let's try 5. If we try 5, then we can see that here, if you have 5, then we know that this is 400. Okay, so let's see if that's going to work. 2a plus 4 is equal to 400. Now we can notice that, well, this one works, right? A is 400 minus 4 divided by 2, or we can say 198. Okay, so now this one works. Okay. Yes, hold on, guys. I will. Okay. So now, okay, if you have any question, please let me know. Yes, 16 marks, right? So now we can, okay. So we're going to see what's going to work here, right? Now we can see that here, even times even is not going to work, right? Why is that? Because remember, when n is odd, we can odd times even. When n is even, we get what? When n is even, we get even times odd. So we are only looking for different parity products, right? Odd times even times odd. We cannot have, as you can see here, even times even, okay? So I hope that makes sense, okay, guys? So now, that means the only thing that is going to work is gonna be, okay, so we can write it, the only thing that is going to work, odd times even or even times odd. No even times even, okay? Now let's see. For example, we can have 10, but if you do 10, then we can get that this is 200, and that is not going to work, right? Okay? So the only thing is gonna work when n is equal to 1, right? We can check, guys, if you're interested. So you know that after 10, the next one is gonna be what? 16. We have 16 and 125. This one does work. So please do not make an assumption that the value n cannot be even. N can be even, but it cannot be even times the second, this part here cannot be even times n. So we have 16 times 125, right? And then the next one that is going to work is 20, right? 20 times 100, but you know that this is not going to work, right? Okay. I hope that makes sense. Now, so by looking at this, again, we are looking for different parity, right? So what is the next one? For example, we can have 25, okay? We can have 25 times what? 80. And this one works, right? And what is the next one? We have 50. If you do 50, it is going to be 40 here, and you know that this is not going to work, okay? I hope that makes sense. So the only one that is going to work is when n is 1, when n is 5, okay? When n is 1, when n is 5, when n is 16, and then 25. And we just established that 50 is not going to work, and it cannot be, it cannot be, sorry, it cannot be 50, right? And now what is it? It cannot be 100, right? And now what is the next one that is going to work? 1, 5, 16. Yes, there is a faster way. We are going to get to that. 1, 5, 16. What else? Can someone tell us what else it works? Okay, you can write it. 125. What else? What else? 80. Does 80 work? Yes. What else? And then we can find out, we can go backwards. So it's 400. And then what else? Can it be 2000? Does 400 work? Does 2000 work? Can we have 2000? Because now a wouldn't be an integer, right? There's no negative, okay? 2000 is going to give you, let's say 400 works. If you have 400, then you have 2a plus 399 is going to be equal to what? 50. Does this one work? I'm sorry, 5. Does this one work? No, right? Sorry, it's lagging. This one doesn't work, right, guys? So now 400 does not work. We are looking for positive ones, okay? So we know that this doesn't work. Okay. Yes. So now we can see that 1, 5, 15 does 125 work? Does 125 work? No. 125 also allows a to be a negative number, so we can see that 125 also doesn't work. Does 80 work? No, right? 80 doesn't work either. Okay? So the only thing that is going to work is going to be what? 1, 5, 16, 25. Okay? Oh, 8. Sorry, I forgot 8. How can I forget 8? Thank you, guys. 8 does work, right? Thank you. Okay, so now we can see that how many numbers do we have here? 1. We have 1, 2, 3, 4, and 5 numbers, right? Is that okay? Oh, 8 doesn't work. Yes. Thank you. So I was correct. Someone confused you. So we have 1, 5, 16, 25. Sorry. Because it's 8 times, then it's the part is. Okay. Yes, I took out of 8. Thank you. Now we can see that we have 4 of them, right? Again, what we eliminated was, we eliminated the ones that are even times even, right? Okay. Okay. So because one of the product has to be even, right? Now what we can say is that because one of the product has to be even, the other product has to be odd. If this is even, this is odd, and so on, right? So basically, in these questions, we are looking for the number of odd positive divisors for 1000, right? Okay. Okay. So in this case, we only allow. Okay. We only want the odd factors, right? Because we want one of them to be even, one of them to be odd, okay? So if you take a look at here, how many odd divisors does this number have? We have 4 odd divisors. How do we find this? We only find when you get rid of what? Just close, oops, sorry, it's lagging, guys. Just, we're gonna ignore this 2 to the 4 part, right? If we do, ignore the 2 to the 4, because we are only interested in odd divisors here, 5 cubed. How many divisors does 5 cubed have? 4 divisors, okay? So that's why, if you take a look at here, oops. Okay, so we are only interested For 1000, right? For 1000, it is 2 to the, I'm sorry, 2000, it is 2 to the 4 times 5 cubed, right? Because we're only interested in the odd multiples, the odd factors, just ignore the 2, right? Because anytime you multiply a number by 2, you make it even. So for 5 cubed, we have 4 divisors. So that's why, that means that we can have only, n can only take 4 different positive integer values. Parity means odd and even. Okay. Okay, guys. So I hope that makes sense. Okay. Next problem here that we're gonna solve, right? Okay, I will actually skip this one. We just did that. Okay. Let's try this sum here. Okay. Okay, so let's try this one. I skipped the number 2, it was similar. So I'm going to try a few different problems here. So what about this problem here? Again, this is just a summation problem. Here, this is in the general form of what? We are going from n times n plus 1, right? Similar to triangular numbers, and we know that n is going to be from 1 to 100. Do you guys see the general term here? If this number is n, that's the pattern, right? And this is equal to n squared plus n. So basically, we can say that 1 times 2 plus 2 times 3 all the way to 99 times 100. We can write it in terms of what? So we can write this as 1 squared, 2 squared, all the way to what? 99 squared. Or can be what? n plus n is what? 1, 2, 3, all the way to plus 100. Okay? What is the sum of the squares? Does anyone know what the sum of squares numbers are? It is equal to what? N times n plus 1 times 2n plus 1 divided by 6 plus n times n plus 1 divided by, I'm sorry, this is goes to 99. Okay? And now here, you can factor out n times n plus 1 over 2. We get 2n plus 1 over 3 plus 1. That doesn't, you don't have to, you can just. What is n times n plus 1? 99 times 100 divided by 2. 2 times 99 plus 1 plus 3 or over 3. Okay. I hope that makes sense. Yes, what did you get? 4950. Which one is 4950? The top one, yeah. So now we can see that here. I hope that makes sense, everyone. So in this case now, it is 9 times, multiplying. Now in here, 2 times 99 plus 4 is going to be equal to what? 202. What is 202? Yes. Thank you. 99 times 100 over 2 times 202 divided by 3. Okay. So we can simplify. This is 101, this is 1, this is 33. Okay. So now what is this equal to? You guys can find it, I'm sure. 303 something. What? Oh yeah, 33 something. I forgot the 101. Is it 333300? Should I believe in community? Yes. Okay. You guys probably can multiply better than me. Huh? So we have 3 Oops, it is lagging us. 33300. Okay, so that was the answer. Okay. Next one. Oh, sorry about the LaTeX part here. Next one, we have a question here. S of n represents the sum of the first n positive integers. Let's call a number n a fantastic number if both n and S of n are perfect squares. For instance, 49 is a fantastic number because S of 49 is equal to 1 through 49 is 1225, and 49 is a 7 square. Find a fantastic number greater than 49. Let's try this problem here. Okay, if you have any, so I'm just giving you a minute so you guys can try it, okay? If you have any questions, you guys can. Yes, Kwan, I can see you. You can put it, I enable the chat one. Edward Chen is, Edward, that is the one that I got. Okay, that's correct. Okay, so it's 1681, yes, that is correct. Okay, so now I stop the chat, guys. Okay, so we know that we want, so what we want is that you want this, let's say we have a number S of n, right? So you look at the example, right? So let's say S of n represents what? 1 plus 2 plus 3 all the way to n, right? Which is same as n times n plus 1 over 2. I want n times n plus 1 over 2 to be a perfect square, but I want n to be a perfect square as well, okay? So we're gonna let n to be some perfect square k square, okay? So therefore, because that's what the question wants, so that's what the definition of a fantastic number. So that means S of n, which is same as S of k squared, is equal to k squared times k squared plus 1 over 2. Okay. Now, we want this to be a perfect square, right? Okay. We know that k squared is already a perfect square. So therefore, basically the question is asking us, because this one is already a perfect square, so the question is asking us k squared plus 1 over 2 to be a perfect square, right? Okay. So now, let's do it again. Let k squared plus 1 over 2 to be some perfect square, or not m square, I'm sorry. Let's call it some m square, okay? Now, this means, oops, sorry. Now this means k squared plus 1 is equal to 2m squared, right? Okay. So this means k squared minus 2m squared is equal to -1. Or 2m squared minus k squared is equal to 1. Okay. Now, in the question, we are given an example that's 49, right? Okay. Basically, k is 7, and in this case, m is 5, right? That's what we are given an example. But this is what we are given, right? Okay. Now, what we can do is that, so let's see which other value is going to be satisfying this, okay? In the example, we can see that, okay, in the given example, let me write it with the black color. In the given example, k is 7, m is 5, okay? This is what it's given. Now, what I'm going to do is that I will basically say that, so I'm going to write this as difference of squares, okay? Oops. So let me write this as difference of squares. K minus m root 2 times k plus m root 2, and that's equal to -1, okay? Again, if you plug in 7 and 5, you will see that this is going to work. Now, because I know that this example works, 7 minus 5 root 2 times 7 plus 5 root 2, we can see that that works. Okay? So now, but the thing is, I want to multiply this with something, and obviously we're going to divide with something, okay? So we can see that what others might work here, okay? Now, if I multiply this with 1, and the left-hand side with 1, on the right-hand side and left-hand side both with 1, I'm not changing anything. But let me write this with red color. Okay? Now, but the thing is, I want to multiply this in such a way that I can basically rationalize and I can get rid of the squares and I can find some other values, right? So instead of 1, I'm going to multiply it. I'm still going to multiply by what? By 1. But I'm going to write this. 3 plus 2 root 2, 3 minus 2 root 2. Because obviously, this is equal to 1, right? And that's still equal to -1. Now, why did I do that? Because now notice that 7 plus 5 root 2 times 3 plus 2 root 2, that is going to give me 41 plus 29 root 2. And then the other one, then this part here, the one with the green, I mark it with green, is going to give us 49 minus 29 root 2. And you can see that this is also equal to -1. So therefore, we can see that now our k, another value that I found, was k is 41, n is 29. So that means n is 41 squared, which is 1681, is another number. Okay, so this was another way to find, but obviously you guys found it earlier, 1681, right? Okay. Yes. You guys can write. I see you're raising your hand. Ifan, I see you're raising your hand. Why are you raising your hand? Yes, it will be. Okay, any questions so far? Good. The class answered 3 or 5 today. Okay. Why did we do the stuff in blue? Oh, because so that it will allow me to find another value for k and m. Oh, it's Lake. Oh, I see Lake Como. Hey, Lake Como. Okay, so now let's continue. Okay, before we continue with the next problem, let's talk about some other ways here, right? So now, let's see that, by the way, for those who are would like to know the formulas, right? So we know that these are the triangular numbers, right? This is n times n plus 1 over 2. And then when we do the sum of the first odd numbers, this is n squared. And then the sum of squares, this is 1 over 6 times n plus 1 times 2n plus 1. And then the cube one is going to be equal to n times n plus 1 over 2 squared, for those who really enjoy the formulas. the part that with the square, it is called square pyramid numbers, right? If you have like 1 and then you put, let's say it's like this. If you have like, imagine like a 3D, you can make it like a different shape of square pyramids. If you have a building block, just remember how you can make the square pyramid, right? Okay. So that's how we get those sums. Okay. Again, for those who are really want to know the formulas. Now, the next part that we will talk about is like the prime numbers, right? Okay. Yeah, I did cube. Yeah, 1225 does not work, I think, right? Does it work, 1225? It doesn't work. Okay, so let's move on to a few things. So we know that most of the positive integers can be expressed as a product of the smaller ones, right? And we know that those products, for example, 2 times 3 and so on, we can see that those are composite numbers, okay? And the numbers that cannot be expressed this way, right? Okay, it's called the remaining numbers basically, but other than 1, remember, okay? And those are called the prime numbers, okay? And prime numbers is, so it's like a lot of mathematicians in the history worked prime numbers, right? And then we can see that, I'm sure, especially if you study the art of problem solving books, or if you use sure you've seen this, that remember we write the numbers and then we eliminate all the ones that are multiple of 2s, that are multiple of 3s, and then so on, right? Okay, so you go through this with each prime numbers, okay? And then, so that's, I'm sure you guys seen that, okay? Now, we can see that for the prime numbers, by the way, 1 is neither prime nor composite, right? You can call it like a unit number, okay? And now, whenever we have a prime number, we can write the numbers in that mod prime, let's say mod p, and we can see that we can have any mode, we can write any mode number, we can add, subtract, or multiply, right? But the thing with the prime is that we can also divide. Let's say with the prime numbers, okay? Let's say we are gonna look at mod 7. Again, mod 7 means the residue when you divide by 7, right? Okay, for example, in mod 7, let's say we have 2 times 4. We can see that 2 times 4 in mod 7 is equal to 1, right? And we also know that 3 times 5 is also equivalent to 1. And we know that 6 times 6 is also equivalent to 1. So we can say that, I'm sure you guys seen this before, but it is all right to say that 1 over 2, this part is taken from the Dr. Conway's book, 1 over 2 is equivalent to 4, 1 over 3 is equivalent to 5, and 1 over 6 is, or we can say this, right? Or we can say that 1 over 5 is equivalent to 3, and 1 over 6 is equivalent to 6 in mod 7. Okay. Okay. Now, by looking at this, let's say that I know 1 over 3 is equivalent to 5 in mod 7. Then 2 over 3 is going to be what? It is 2 times 5, which is equal to 3 in mod 7. Okay. Okay, guys? So, and now we can say that, so for example, 2 over 3, so we can continue to write this, right? 2 over 3 is equivalent to 3. 2 over 4 is equivalent to 6. 2 over 5 is going to be equal to what? 3 times 3, or, right, because of here, I can write it here, or equivalent to 2 in mod 7. 4 over 5 is going to be equivalent to what? Is going to be equivalent to 5 in mod 7. Okay? We can write that. Yes, this is like an inverse mod. Okay? So now, I hope that makes sense. So for example, 5 over 6, mod means the remainder. For example, like if you can consider a clock, right? For example, in military time, they say 13 o'clock. That means 1 o'clock, right? So we subtract every 12. So it's similar. Okay. Now, this is how I got it, right? So what I did was, we divided here, okay? Now, for example, for 5 over 6, we know that 1 over 6 is 6, right? Okay. Now, I hope that makes sense here. For example, 2 over 5. So what is 5 over 6 going to be? 5 over 6 is going to be 2 in mod 7. Okay. How do we get that? 5 over 6, we get that is because 1 over 6 is, let me write it. This is, because 5 over 6 is going to be 5 times 6, right, because of here. And there is going to be 30, and 30 is 2 in mod 7, okay? Now, what about 1 over 7? Can we write 1 over 7 in mod 7? No, right? Because why? Because we cannot have 7 in mod 7. It will be 7 is 0 in mod 7, so that would be dividing it by 0. And we cannot divide by 0. Okay? Okay, so I hope that makes sense, guys, okay? This was like, this is, I mean, this is just basically how we can write the fractions in mod P, meaning that where P is prime. Okay. For example, let's say if I want to find 1 over 2, 1 over 3, 1 over 4, blah, blah, in a certain mod, right? Or we're going to check, is there a number 1 over 8 in mod 101? Okay. For example, let's check, okay? So I'm going to check if there is a number okay, 1 over 8 in mod 101. 101 is prime, right? So that's what we're going to use. First, you are going to find a multiple of 8 that exceeds 101, right? Let's find the first multiple. What is the first multiple of 8 that exceeds 101? That is 8 times 13, which is equal to 104, which is equivalent to 3 in mod 101. Okay. I hope that makes sense. This is the first number that exceeds this is the first multiple of 8 that exceeds 101. Okay. So we know that 8 times 13 is equal to 3 in mod 101, right? Now, the first multiple of 3 after 101 is what? 3 times 34, and that is equal to 102, and that is equal to 1 in mod 101. So that means, again, 3 times 34 is 1 in mod 101, right? So therefore, 8 times 13 is equal to what? 8 times 13 times 34 will give us 1, right? So we know that, let me write it. So we can say that 1 over 8, okay? So let me write it again. So we can say 8 times 13 times 34 will give 1 in mod 101, right? Okay. So that means 1 over 8 is equal to 13 times 34 in mod 101. Okay. And we can see that there are 3 34s in 1, right? So 12 34s are 4, 13 34s are 38, and so on, right? So we know that 1 over 8, what is 13 times 34? It is equal to 38 in mod 101. Okay. So there is a number, okay? Because, oh, sorry, Camille, I didn't see. 1 over 3 equals 5 in mod 7, because we know that 3 times 5 is equivalent to 1 in mod 7, right? 3 times 5 is 15, and it leaves a remainder of 1 when you divide it by 7. So therefore, 1 over 3 is equivalent to 5 in mod 7. That's why. I hope that makes sense. Okay. Okay, so now let's talk about, have you guys heard of the Mersenne's number or primes? Okay. I hope you guys, oh, sorry, I think I saw it a little late. Okay. Now you can write in, guys. For example, let's say, I'm sure you guys heard that 2 to the n minus 1 form, right? Okay. Now, Mersenne is that, so we're gonna see if the prime numbers can be in the form of 2 to the n minus 1, right? Okay. We can see that this works when it is 2, 3, 5, and so on, right? Okay. But the thing is, okay, so this one here, okay, let me write this, it's Mersenne. Numbers, okay? Yes. Okay. Now, in this case, so we can see that, first of all, not every number in this form is going to be prime, right? So we can see that 2 to the n minus 1 is not prime if n is not prime, right? Okay. For example, let's say, for example, 2 to the 5 minus 1. It cannot be prime, right? Okay. Does it make sense? Like, sorry, not this one. What I mean is 2 to the 15 minus 1. Okay. So we can see that here, for this to be, so if n is not prime, 2 to the n minus 1 is not going to be prime. Okay. I hope. By the way, you can see that this is not prime if you write this number in binary. But there are also prime numbers where 2 to the p minus 1 is not prime. So the reverse is not true. Does it make sense, guys? So for 2 to the n minus 1, if n is not prime, 2 to the n minus 1 is definitely not prime. But this doesn't mean when n is prime, then the 2 to the, let's say, 2 to the p minus 1, this is not always prime. I can give you an example. 2 to the 11 minus 1. That is equal to 2047, and that is 23 times 89. Okay. Okay. But, for example, let's, so for example, where we can say that, so this was about the Mersenne prime. So let's say that, do you guys know that you heard about perfect numbers, right? And now, you know that the perfect numbers are numbers what? When the sum of its prime divisors equal to the number itself. Right? For example, let's say 6. 6 is equal to 2 times 3, right? The divisors are 1, 2, 3, and 6. If you look at its proper divisors, 1 plus 2 plus 3, that is also equal to 6. Therefore, 6 is a perfect number. Okay? For example, 28. 1, 2, 4, 7, and then 14. 28. This is also a perfect number. Okay. And now, the thing is, so why I mentioned that, because there's actually a connection between a perfect number and then the Mersenne primes, okay? So let's say that we have a Mersenne prime n, which is 2 to the p minus 1, okay? Then that means, okay, if this one is a prime number, let me write it in a better form, guys, sorry about that. If n, oops, is equal to 2 to the p minus 1 is a Mersenne prime number, okay, then the nth triangular number is a perfect number, okay? Remember the nth triangular number is what? 1 over 2 n times n plus 1 is a perfect number. Okay? For example, 31, right? N is equal to 2 to the 5 minus 1, which is equal to 31. It is a Mersenne prime, and the 31st triangular number, let me write as t sub 31, that is equal to 31 times, so the 32 divided by 2. Okay. This is equal to 496, and then 496 is actually a perfect number. Okay. It's gonna end now, okay? No, it's just, that's what it shows. Okay, guys? So this is just an, oh dear. Okay, so I will stop here and I will continue next Tuesday, okay? It's not Tuesday, it's just, I don't know, for some reason, whenever I share the screen with Zoom, it's stop the time is Tuesday, January 9 at 9:41, okay? Okay, guys, so I'm gonna stop here. Thank you so much for joining us. I hope it was a good 1.5 hour time spent, okay? Thank you, guys. And the Thursday session is more advanced. It's more only for later AIME and JMO level.